Hello, this is Dr. Dave Storms. Since we're a little behind in class, I'm going to finish the lecture on orbital hybridization using the Explain This app and post it online. That way you can watch it and have it available to you. And so we're going to be looking at how to explain the orbital hybridization in alkynes, in particular these sp orbitals. So you need to, sorry about that, you need to realize that, or the example that we're going to be using is ethine. I've already put the chemical formula for ethine up there. It's C2H2. It's also known as acetylene. Okay, and we have to remember that I'm going to show the energy levels for one carbon, but we have to multiply it by 2. So we have 2 carbons, but each carbon, remember, it has 4 valence electrons. 1, 2 of them will be in the s orbital. And then we have the 3 p orbitals, but only 2 of them are half filled. These are all p orbitals. Before we can even bind the carbon together or add in the hydrogens, if we left it here, remember each carbon is going to be bound to one hydrogen and the other carbon. But if we left it here, we would have this empty p orbital. So whenever we start to add in the other electrons, we have 2 electrons either from the other carbon or from a hydrogen that would be in this empty p orbital hooking up with themselves. And so we know that's not true because we have bonds of equal lengths between the 2 carbons and each of their hydrogens. Okay, so what happens instead is if you just add a little bit of energy, we can pop one of these electrons from the s orbital up into this p orbital. So I'm going to draw that in now. Remember, we're multiplying everything by 2. So we still have the s orbital, but now only one carbon electron is in there. We still have 3 p orbitals, however now they are all half filled. Now each carbon is going to be bound to 1 hydrogen. In order to, let me try to see if I can find a good picture of what I mean. Let's see, let's look at this one. There we go. So if you notice here, each carbon is bound to 1 hydrogen, and then it's making a total of 3 bonds to the other carbon. So, since each carbon is bound to 2 other atoms, that means that we only need 2 hybridized orbitals. So, when we start to add in the hydrogens, remember each hydrogen is bringing in 1 electron, and each hydrogen will be bound to 1 carbon. So what happens is, instead of having an s in a p orbital, we have what's called sp. And it's going to have 50%, it's going to be halfway in between in energy. It's going to have 50% s-like characteristics and 50% p-like characteristics. We still have 2 p orbitals that are half filled. There's an electron from each carbon that's occupying each of these orbitals. So, now we can add in 1 hydrogen. Remember, this carbon, if we call it the left carbon, it's bound to 1 hydrogen. The other 3 bonds are bonds that are making with the fellow carbon. Okay, so let's now draw this as a cartoon. I'm going to draw the first carbon, and it has 2 sp orbitals. They're going to look like little short, fatty looking dumbbells. sp, sp. one sp orbital is interacting with the hydrogen. The other sp orbital is interacting with the other carbon. Now, please note, there are still two empty p orbitals. I'll draw one in this color on each carbon. Whoops. I'll draw one. Let me try this again. In that color with each carbon. And they're interacting with each other. That could be the PY. It doesn't really matter what we'll call it. Likewise, we have two more that's orthogonal. I shouldn't say two more. Remember, it's a single set of dumbbells makes one orbital. It's just two lobes, and they're interacting. So we actually now have a triple bond. We have this, that's a sigma bond, one pi bond in that color, and one pi bond in that color. Makes a triple bond. Now, if you would like to see a picture of it that's better than my cartoon drawing, then we can go over here and add in this is what I was trying to show. We have the carbon with the sp orbital overlap between the two carbons. Each one's bound to a hydrogen. We have this colored p orbital with overlap, sideways overlap. This colored p orbital and sideways overlap. Or if we would like to see another picture of it, we can look at it this way. This one shows how the orbital shapes would be. They are perpendicular with respect to each other. So we can see there's one that's kind of up and down, and then one coming in and out of the plane of the iPad here, of the board. And then we see the sigma bonds, one of what's between two carbons and the one between each carbon and a hydrogen. Hopefully this helps explain sp hybridization.